So for today's lesson, what we're going to do is talk about simplifying radical expressions. And a radical expression is just an expression that contains a radical, which is either a square root, a cube root, or some other root. But we're really just going to concentrate on square roots. And square root is this particular symbol. They actually call that a radical symbol. Whatever number or variable is under that radical symbol happens to be called the radicand. So a radical expression is in simplest form when no perfect square factors other than 1 are under that radical. Okay, so no perfect squares other than 1 are in the radicand. You can't have fractions in the radicand under the symbol, and no radicals can be in the denominator of a fraction. When you simplify radicals, the idea is you want to find the largest perfect square that divides evenly into the number that's under the radical sign. You're going to write that number under the radical sign as a product of the perfect square, and the answer resulted from dividing that. All that basically means is you're going to use this product property of square roots. If you've got two numbers under the radical, you're going to find the largest number that's a perfect square, and then you're going to find the other number that divides into what you're looking at. You're going to find the square root of the perfect square, and that number is what goes on the outside. So you take the square root of the perfect square, and that goes on the outside. The number that you can't touch, that's not a perfect square, stays under the radical sign. Okay, and that's because it's irrational. If you have other numbers outside the square root symbol, you're going to multiply those. If you have variables, in order to be a perfect square for the variable, the exponent has to be even. If it's not even, then I'll show you how you're going to figure out the exponent in a few seconds. And then again, make sure that no terms under your radical sign are divisible by a perfect square. Okay? So the product property of square roots is when you have one large perfect square and you break it up into two separates. The quotient property of square roots is when you have one big radical and you break them up into two separates. What's really important to know is the square root chart. And the idea is this, and we're going to put a blank sheet of paper up here. If you were to give yourself like a T-chart, and then you were to write all the counting numbers, I don't know what just happened there. If you were to write all of the counting numbers, let's say from 1, let's see how far I can get, 2, 3, 4, 5, 6, 7, 8. We'll stop at 10. These are all your counting numbers. If you squared all these counting numbers, then you'd be looking at 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. All of these numbers in the second chart are considered to be perfect squares. All these numbers on the right side of your chart tend to be their square roots. So if somebody said, okay, well 81 is a perfect square. What's its square root? You would say 9. And if somebody said, well, what is 5 is a square root of what larger number? You'd say 25. Okay, so you need to basically have a chart like this, and you're going to use this to help you divide into the numbers under the radical. Put this chart somewhere to the side. Let's see what we can do. Simplify and use your square root chart to help. Well, I know that if I use my square root chart and I looked at the number 18, I'm going to go back for a second, and I asked myself, what's the largest one of these perfect squares that divides evenly into 18? I think you would say the answer is 9, because 9 times 2 is 18. And then what you would do is you would use the product property, and you'd say, okay, the square root of 9 is going to be the square root of 9 times 2, because I can use the product property. Well, the square root of 9 is just 3. That comes on the outside. The square root of 2 is not a perfect square. It's irrational, and my answer just stays as 3 radical 2. 75. Well, what's the largest perfect square that goes into 75? As you use your chart, you should see that it's 25. So 25 times 3 is 75. So then what you would have to do is make this into two separate radicals, the first radical being radical 25 times radical 3. When you look at the variable, it has an even exponent. So that's great because that means that is a perfect square all of itself. So x to the 6th. Square root of 25 is just 5. The square root of 3 can't be touched. Well, the fact that this exponent is even, the square root of x to the 6th is just half of its exponent. So the square root of x to the 6th is just x to the 3rd. And this would be your final answer. As long as your variable is, your exponent is even, you cut it in half and that's its square root. Let's try another one. 3 times radical 24 x to the 5th power. Well, in terms of the 3 on the outside, it can't go anywhere. It stays where it is. In terms of the perfect squares that divide evenly into 24, 4 is the largest perfect square that divides it evenly. 6 is the other factor because 4 times 6 is 24. Well, x to the 5th is not even, but if I subtract 1 from 5, I get x to the 4th. So if I want to rewrite x to the 5th as a perfect square and a not perfect square, I would say x to the 4th times x. I still have here, just need to understand, this is still 24x to the 5th under a square root. I just used that product property. Now I start taking my square roots. Again, this 3 can't go anywhere. This is a perfect square. A 2 is going to fall out, but remember it's all multiplication. This is a perfect square. Divide my exponent in half, and this becomes x squared on the outside. I can't touch the stuff underneath that are the 6 and the x, so they stay under. Final answer would be 3 times 2, 6x to the 2nd, times the radical of 6x. Next one, negative 2/3 is on the outside. The negative 2/3 doesn't go anywhere. I'm going to keep that here. When I use my square root chart, I realize that 36 is the largest perfect square that divides into 72 times 2. Well, the square root of 36 is just 6. When I now multiply 2/3 times 6 over 1, be careful with your fractions, it becomes just negative 4. And I can't touch the radical of 2. Let's see what else we got. Here's division. Remember, quotient property says break these square roots down into 2 separates. So what happens on the first one, the square root of 4/9 becomes the square root of 4 over the square root of 9. Square root of 4 is a perfect square. Square root of 9 is a perfect square. My answer here is just 2/3. When I break square root of 8/16 down, I get the square root of 8 over the square root of 16. Well, my denominator is clearly a perfect square. A 4 drops out. But my numerator isn't. However, divisible by 8 is this perfect square of 4, and then this other number, which is a 2, which is not a perfect square. Well, the square root of 4 is just a 2. So that leaves me with this, 2 rad 2 over 4, but that then becomes 1 rad 2 over 2. Wherever you can simplify stuff, you need to, and you can only simplify things both in the radical or both out of the radical. Let's try another one. Root 75 over root 25. Well, root 75, root 25. What's nice is my denominator is a perfect square. Its square root is 5. 75 can be rewritten as radical 25 times radical 3. The square root of 25 is just 5. This now becomes 5 radical 3 over 5. Those 5's cancel out, and my answer is just radical 3. This should be, I think, the last one. Rad 12 over rad 36. Well, rad 36 is just 6. Rad 12 can be broken down into rad 4, rad 3. Rad 4 is just 2. I'm going right to the simplified form. 2 over 6 is just 1/3, and I can't forget that I've got a rad 3 still in the top. Now here's the deal. The 1 is not necessary. If you wanted to just have your answer as rad 3 over 3, not a big deal. Okay, so that's it. I think the next thing is homework, and you should be, yep, so it's homework and you should be good to go.